So in your packet, you should have a table that looks like this, and this is just for taking notes and just to keep things organized. So as we go through this next little section, you can do this as part review and part new information. So let's start off with hydrogen. So hydrogen doesn't really have a family. It's put over the alkali metals because it has one valence electron, but that's really all the similarity that is there in that family. Also, it does end in an S1. So for those two reasons, that's why they put it there. But it's really its own family because it's not a metal, even though it's over those alkali metals. All right, so what do we know about hydrogen? So it is the simplest of the atoms. The majority of the isotopes of hydrogen just have one proton and one electron. It does make up most of the atoms in the universe and also the mass in the universe. And most of this is located in stars and giant gas planets. It is the starting point of fusion. We've already talked about that before. On Earth, it is a diatomic molecule. So remember, diatomic, it means two atom. So hydrogen always has to have a buddy. So if it's not with a different element, then it will buddy up with itself. So we call it H2. This is hydrogen. So what are some of the uses on Earth? So we use it to make margarine. So we take oil and we make it a solid by adding hydrogen. It's called hydrogenated oil. Ammonia is used. Ammonia has three hydrogens bonded with a nitrogen, and also we see hydrogen in rocket fuel. When we look at the reactivity of hydrogen, hydrogen can lose its electron. When it does that, it becomes a hydrogen ion, and it looks just like this, an H plus. And I just did a simple formula here so you could kind of see. So we have hydrogen chloride, and then that electron comes off. It leaves an H plus left. So really it's just a proton. And then we have the ion that took hydrogen's electron. Also, hydrogen can share its electrons. So a good example of this is with water, H2O. We find sharing right here. So when you look at oxygen, oxygen has 6 valence electrons, and 2 of those valence electrons are used to pair up with hydrogen. So this gives hydrogen a noble gas configuration because it's able to have 2 electrons, just like helium, and oxygen sharing with hydrogen is able to have a full octet, or 8 outer electrons with sharing with hydrogen. So that gives it a special stability. So this is why hydrogen and oxygen bond. Another thing that we can see hydrogen doing is taking an electron, and it does this with metals. So metals give up their electron and hydrogen is able to take that. And so when it does this, when it gains an electron, it's called a hydride ion. So if you have an anion, the name changes. You add an IDE to the end of the element name. So this hydrogen, you drop the ending, it would be IDE. So hydride ion. So this occurs when hydrogen bonds with the group 1 and group 2 metals. So your alkali metals and your alkaline earth metals. And so a good example of this is lithium hydride. So lithium gives up its electron to hydrogen and we get that H minus. So as far as your chart goes, what do you know about hydrogen? Hydrogen has one valence electron. Its electron negativity ends in S1. Its electron configuration is 1s1. But those are some of the uses of hydrogen. All right, let's go to the alkali metals. And so we're going to look at the main group metals. So not the transition metals, the main group metals. So the alkali metals are group 1 and group 2, and there are also some metals in the P sublevel. So when you look at your P sublevel, so it starts with boron here, okay? So it looks something like this, but you have that little stair step that goes across. So these guys right here, these are metals. All right. So let's just keep that on hold and we'll start with the alkali metals. So alkali metals have an oxidation number of +1. Your alkaline earth metals, they have oxidation number of +2. So what's going on with the alkali and alkaline earth metals? So you're filling the S sublevel. These metals are a lot softer than the transition metals. They are still metals though. They conduct electricity. They're very, very reactive. And the most reactive metal is francium. So that's something important to remember. And then these little P metals, or the metals down here in this little corner, they're most of them are poisons. So this is called poisoner's corner. Okay. I will put the links to these videos on Canvas after this video. So take a good look at these. What happens with alkali metals when you put them in water? All right, let's look and see why francium is so reactive. So I've mentioned this before, but francium has something called shielding effect. So look at all these electrons that I have in francium, and let's compare it to lithium. So both francium and lithium have only one valence electron. So here it is, one valence electron. So when you look at lithium, lithium's nucleus very, very easily can keep track of its 3 electrons. But look at francium's uh, valence electron. It has to somehow go and wade through all these electrons here to try to pull on that valence electron. And it's kind of hard to do. These inner electrons act as a shield. So I'm just writing the word shield there. So the nucleus's pull on that one valence electron, it's weakened. So as a result, anything that is close to francium is able to rip that electron off francium. So this makes it extremely reactive. So it's our largest atom, and it is our most reactive metal because of the shielding effect. All right, so let's look at which of these has more shielding effect. And again, the more shielding effect with your metals, the more reactive it's going to be. Now, some of these are not metals. So I'm looking at the first example here. These are non-metals. And so with non-metals, it's a little bit different. The greater the shielding effect with non-metals, then the less reactive. So let me just kind of write that out. So if you have a high shielding effect with metals, then it is more reactive. However, if you have a high shielding effect with nonmetals, then it is less reactive. And the reason why is nonmetals are trying to gain electrons. And their nucleus has to reach out and grab electrons from another atom in order to gain that. And because of the shielding effect with these nonmetals, it's not powerful enough to reach through all those inner electrons to try to grab more electrons. So as a result, the more shielding effect with nonmetals, the less reactive it's going to be. Okay. All right, now let's look and see our first example. So we have chlorine or iodine. So which has more shielding effect, or in other words, which is the larger atom? And it would be iodine. So between chlorine and between iodine, iodine is less reactive because of the shielding effect. Its nucleus just can't reach out and grab more electrons. So chlorine is actually a poisonous gas if we look at elemental chlorine, while iodine is a solid, and it's not as reactive as the poisonous chlorine gas, again because it has more shielding effect. Let's look at our number 2 example. So these are both metals. So the larger of the two is going to have more shielding effect. So we find that barium is further down the periodic table. So as a result, we would predict that barium would be more reactive than calcium because it has more shielding effect. So its outer 2 electrons, very easily they're able to rip off the atom. So some other element will come and grab them. So next we have our number 3, we have xenon, we have neon. So which of these two has more shielding effect? So it's always going to be the larger of the two, and so it would be xenon. Xenon has more shielding effect. All right, let's look at some transition metals. So these are the d electrons, and we have very many Oxidation states, we've already talked about that. Some of the uses of the transition metals, there's coins, catalytic converters, jewelry. They're very, very good conductors. A lot of our building materials come from the transition metals. What's going on? We're filling the D sublevel. So if I were to draw the D sublevel, just be a block like this, okay? And what are the trends? We find that generally as we go across the period, it's getting smaller. Alloys are formed from these transition metals, and alloys when you have a mixture of two or more metals. All right, the lanthanides and the actinides, so they're found at the bottom of the periodic table because they've been cut out. So the lanthanides, these are also called rare earth metals. They are filling the 4F sublevel, and we use a lot of lanthanides in our electronics. So that is something important in our world. Your actinides, these are all unstable. They are radioactive. Uranium is the largest natural element, and this ceramic color right here actually comes from uranium. They added uranium to the paint that they used for these dishes. And they are very radioactive. In fact, collectors, they keep them in a gun safes because it has a lead lining to try to absorb the radioactivity. So I don't know if I would want to collect that because they are radioactive. Also, in the early 1900s, they would add uranium to glassware, and they noticed that it had this unearthly glow. So anyway, so there are collectors out for uranium glassware. Other things that I have here, we have a smoke detector here. So that your smoke detector usually has a actinide by the name of americium. And if smoke gets in the way of the radioactive particles that are in between the sensors, then it will go off. So that's one reason why smoke will interfere with the radioactivity being received where it is on the detector. And so as a result, the smoke alarm will go off. And last but not least, so some pacemakers have some actinides in it. All right, so let's keep going with nonmetals. So what's happening with the nonmetals? Nonmetals are found on this portion of the periodic table. I'm just going to try to draw it out a little bit here. So again, you have that stair-step line separating metals from nonmetals. What do we know? We know that helium is our smallest atom. So as we go across towards helium, they're getting smaller. And what we're doing with the nonmetals is we are filling the p's, so filling those p sublevels. So they have many valence electrons, so a lot more than metals do. And so they tend to gain electrons when they form compounds. And what do we know about nonmetals? They're brittle, they are poor conductors, so that means they're good insulators. They have lower densities and lower melting and boiling points. In fact, a lot of the nonmetals have already boiled. They are gases at room temperature. So they make up our atmosphere. They make up most of the Earth's crust found in compounds. They can form positive ions with other nonmetals, and we haven't really talked about that, but we will later on. Or they can form negative ions when they combine with metals. And specifically our noble gas family right here, generally they are unreactive. And that's because they have a full S and P sublevel, so that complete octet. And so with nonmetals versus metals, metals mostly have solids, where nonmetals you see gases, you see one liquid, and then you see some solids. And here's just a summary between metals and nonmetals. So metals are ductile, meaning you can pull it out into a wire. They're lustrous, meaning it's shiny. They're malleable, meaning you can shape it. They do conduct electricity in all states, solid, liquid, and gas. They lose electrons, forming positive ions. They have higher melting points than nonmetals. And we already talked about how they form alloys by you can melt two or more metals together. And they have ionic bonding with nonmetals. And we haven't talked about bonding yet, but it's coming up in our future units. Nonmetals are brittle. They are not shiny. They are good insulators. wide variety of properties. So there's a lot of gases, and they can form positive ions with other nonmetals and negative ions with metals. And what are the characteristics of metalloids? Well, they're going to have some of each of these. So looking at this chart, were you able to fill most of it out? Let's just kind of review some of the things. So we know oxygen mostly is a +1. It can form a -1 oxidation numbers. Your metals are all positive. We know that the main group metals can have a +1 or a +2. Your P metals, they can get a little bit bigger. You can have +3, +4, and there's even one that has a +5, which is a little crazy. And then we have our transition metals and our actinides and lanthanides. They have various oxidation numbers. Okay. Let's go ahead and just continue out this column with oxidation numbers. So your nonmetals and your noble gases. So they have negative oxidation numbers. And your noble gases, they do not have oxidation numbers. Let's look at the electron configuration. So we know that hydrogen, whether it's going to gain or lose electrons, is going to look like that as far as its atom goes. For the electron configuration for your metals, if I look at your main group metals here, so you have your S1 family, you have your S2 family, and then you have your P1 family, your P2 family. There's even like a P3 guy. Okay. All right. And your lanthanides and your actinides, you know here that these are your Fs. Okay. Is what their electron configurations are going to look like. Your your nonmetals and your noble gases. So you just draw that portion of the periodic table. Okay. So the electron configuration, so we're filling the P's, and we do know that the noble gases will end in a P6. Okay. All right, electrons in the outer energy level. So these are valence electrons. So hydrogen just has one. Your metals have one or two. You do have some of those P metals. They can be a little bit higher. The ones in that little corner of your metals. For your nonmetals, the electrons in the outer energy level, they should be higher numbers. So we can get 4, 5, 6, 7, 8 are the number of valence electrons. Okay. Your noble gases, of course, have the 8. The radius, so generally the trend, you don't need to fill anything in for hydrogen. You're not comparing it to anything. But for your metals, if I draw them, generally as you go across, it's getting smaller. As you go down, it's getting larger. So your nonmetals and your noble gases, the trend continues. As you go across, it's getting smaller. As you go down, it's getting larger. Reactivity, so we know hydrogen can gain electrons, gain one electron, it can lose one electron, and it can also share electrons. So kind of hydrogen's multi-uses. Reactivity for metals, we know that francium is the most reactive metal of all of them. Okay. And we know and the reason why it's so reactive is because of shielding effect, is it has so much shielding effect that it's just really easy for that one valence electron to be lost. For your nonmetals and noble gases, so we know generally these noble gases, they don't react. Okay, so I'm just going to put that they don't react. And then your nonmetals, we know the most reactive is fluorine. And the reason why it's most reactive is because it doesn't have shielding effect. And nonmetals reach out and they grab electrons from other atoms and pull them in. And this is exactly what fluorine's nucleus does. Because there's no shielding effect, it very easily can reach out and grab electrons and rip them off other elements. So for the uses, we already kind of went through those in the slides. So just do your best with this. This is just meant to be a concluding summary chart.